Today I'm going to review this terminal block fuse kit. Now what this is used for and is putting on right on top of a battery terminal and then putting a fuse directly at this joint. So these fuses cost $15 as a kit, as far as you get one bracket and one fuse, and then the additional fuses are like maybe $3 or $4 each or something like that. And here's a typical application of what they're good for. They work on top of the battery terminals. This review is comprehensive and it's a bit long, but I'm going to go through everything, including the power loss, the temperature, how you connect it, and whatnot. Now you can buy these separately or as a kit, and you can buy a variety of different fuse sizes. Now mine's 100 amp because my 100 amp hour batteries actually have a BMS that limits them to 100 amps. And so I'm going to go ahead and match the capacity that they're rated at. They're rated at a maximum of 100 amps continuously. And so I'm going to put this in parallel. Now in the previous video, you saw me do this, and what I had done here is I'd gone down to the hardware store. Actually, I went to the auto parts store, and I got this type of fuse here. And so I did it because I was able to put it directly from this jumper on the positive to positive to the terminal. And a viewer pointed out that I really need a fuse holder because this way, if the battery's bumped or something, then all of the tension would be on the fuse itself. And he is totally correct. I just couldn't find a fuse in the holder in the configuration that I wanted. All the fuse holders had bare wires, and so I guess I could have done that if I could have gotten one with a big enough wire, but I wanted to use a really large conductor between the two of them. So they probably have one that was big enough to do my application. I just couldn't find one locally. So what I want to do is I want to review and test this product as a replacement for an A&L type fuse with a fuse holder. So let's take a look here. I've already tried one of them the other day. So this particular one comes with a spare fuse, and then they want you to put this on the positive side. And so how they're designed is this. They come with a nut, a lock washer, and a regular washer. This is designed to go onto the battery terminal itself. And then you can take off power from this terminal after you put the fuse in. So here's the actual fuse itself. You can see how it gets thin at the point, just like a normal fuse. There's the rating and the voltage, and these go on like this. And then if you put it like this, is the only way it will go. You can see it from the side. So pick the side that you can view from your battery compartment forward. In other words, if this is forward, don't do it like this. Flip it around so that you can see the fuse and you can visually check. Sometimes they don't go in there. You have to kind of give them a little shove. And then now you can put another terminal on top of this and then tighten it down. So the way it works is that they've got a heavy duty, I don't know what that is. It's a little bigger than 1/8. And that is the mechanical connection. And that'll have strength between, like if the batteries get pulled a little bit, that'll give you your strength, and it's heavy enough to carry the current. And then down here, you will see they have got a couple of rubber bushings. The way it works is that this metal part of the fuse, there's the same on the other side, and that metal part goes around the bushing so it does not contact the post. In other words, we don't want it to bypass the fuse. And then when you put this down, here's one connection. It goes through the fuse to the top of this, and this bolt is not connected to this plate. And that's what the rubber insulators are for, or whatever material they used. And so it's important you understand how it works, because at first sight it looks like you're just going past the fuse, but you're not. This is to hold the fuse down and to make good electrical contact with one side of your fuse, okay? All right, so let's get that ready. I'll figure out how I'm going to do this. Let's go look at my battery pack. So the way the batteries fit in my motorhome is like this. So I'm going to put it like this so I can see the 100 amp fuse from this side. And then what I need to do is more than likely create a new connector, because this one probably will not work. No, it will not. So now what I'm going to have to do is take this lug, and I'm going to have to make it a little bit bigger so that it goes down in here, and then I'm going to have to kind of make an L. That's a little bit of a disadvantage that I see with these, is that it makes it high. So if you're taking power off and you're going somewhere, it doesn't really matter because you probably have slack in the cable. However, if you're doing a parallel connection like I'm doing, well, then you're going to have to get a good bend, and it depends on the size of your conductor. And I'm using very large conductors because I want to have very little loss of voltage and a very, very low resistance between the batteries as I can. And I just happen to have a whole big bunch of this 2-aught cable. So I'm going to go ahead and make that, and then I will come back. And another side note is that because I'm using copper lugs, copper cable and aluminum lugs, then you need to put an anti-oxidant joint compound of some sort so that you don't get galvanic corrosion. If you get galvanic corrosion, you could cause a huge problem. What happens is that whenever you have corrosion, you start to have resistance at the joint, and this causes heat. And so it also has a loss of efficiency. And so you definitely do not want to do that. I just could not find any copper mechanical lugs this large. And so that's why I had aluminum, because that's what I could get a hold of. The biggest copper I could find would take like maybe a number 2. And I suppose a number 2 would work. But I just chose to use the joint compound and the different materials just so I could get it. So anyway, I will do that and then come back in a second. By the way, here's my new sweatshirt with the design on the back, and this is also available in my store, and I really like it. Nice warm sweatshirt. So check that out if you're interested. All right, so I've made my connector, and this is so heavy and big I couldn't get quite the bend I wanted to. But I've got my dielectric paste in there, and I put it all around all the terminals on both sides. Worked it in with a brush like the manufacturer recommended. Now, when it comes to electrical connections, you have to be very careful. For one thing, you have to have good, clean connections so that you have a good electrical contact. Second thing is that you need to have it sufficiently tight, because if they have loose connections, what that does is this increases the resistance at the joint, and it will heat up. And I'm not talking about little currents here. I'm talking like 100 amps here and up to 200 amps coming out of the terminals here. So that's not insignificant at all. That's 2 kilowatts. And so when you're dealing with real high currents, the quality of the components makes a big difference. That's why I have such big connections. And so you've got to follow everything and use common sense, and also, follow the manufacturer's instructions. They give you good guidelines on how to do this, and make sure that you know what you're doing. If you do not know what you're doing, hire somebody that knows what they're doing. Now, let's take a look at this connection, and I'm going to tell you a couple things that I like and don't like about it. For one thing, for this particular application going in parallel, I don't like it because I have to go up and over. I like the fact that it's got a terminal here and a terminal there that I can do lugs, but I think I'm actually going to go back to an A&L with with a fuse holder that'll have the biggest wire that I can find. And so I think that's what I'm going to do. And then just have 2 short lugs in the middle with an A&L fuse and go with that. But for the sake of this review, then I am going to go ahead and we're going to load test this. I'm going to put a kilowatt on this, and we're going to measure the temperature and things. Now, for my application, this red protector does not work because of the size of this lug. I can't get it over. If you just had a smaller lug, it might work, but right now it's almost useless. Okay, so now this is loose because I need to go get the power connectors for my inverter. So as in the previous video, I was explaining how to properly connect the parallel wires, and you do not want to take your positive and negative from this end or this end. That's a mistake, because if you did, then you will have almost zero resistance between these terminals, just basically the battery resistance. And then you would have to deal with the resistance of the wire, the resistance of the fuse and everything before this battery could draw, and so it would draw less current through here and more current through here, and I showed that in my last video. So the proper way to do it when you have it like I have assembled is you do the positive in one corner, the negative from another corner at a diagonal, and that forces all the current to go from here to here all to your load, and from here to here all the way to your load, okay? So let me go get the power cables and hook it up, and then let's do a little test. So here's my inverter, and I made this cable. So I bought these copper lugs, and the most I can fit in there are 3 number 10s. And so I've already done load tests, and I can run 90 amps through this, and they stay pretty cool. What came with it are these tiny little, just maybe one of these with like a 40 amp fuse, and I can't understand it because this can run over a kilowatt, and so I don't know why they came with such teeny tiny wires, but I'm not using their teeny tiny wires, so I used another fuse here. So that's another 100 amp fuse on this one, just like I do on the other one, and so that we can protect the output current, and that's just about right for a kilowatt inverter. So first thing we're going to do is hook up the negative. Now don't over tighten, but tighten enough. I'm not sure exactly how many foot-pounds. Okay, now when you're going to connect this, you will get a spark even if the switch is off, because what it's doing is it's charging the capacitors. So let me bring the camera a little closer here. So we're going to get a spark. There's the spark. All right. Now it's charged the capacitors. We are now ready to go. We could, all right. So 13.3, this is our voltage. These are at about maybe 60%, something like that. Now here is our test load. We got this heater. So this heater is a 1500 watt heater, and it has 3 settings. So in my motorhome, I've already done this test, and unfortunately I don't have a current meter that I can show you with, but setting number 1 is about 600 watts, and setting number 2 is about a kilowatt, sometimes up to 1100. It fluctuates a little bit. So this is going to be, I can't remember, like maybe 50 amps, and this one here is about 90. And so this inverter is a bit of a mystery to me. It's made by Livuan or something like that, and it has absolutely no ratings on it whatsoever. It says power inverter, and it shows you the power rating of the USB, and that's it. There's no model number, there's no manual, there's nothing. So I went on to the LiveUAN website, whatever you want to call it, and I saw one similar that was rated at, I think, 1200 with a 2000 watt surge. I took this apart and I found 4 50 amp fuses, and that's probably the 2000 watt surge that it is capable of, but I already know it'll do a kilowatt. So let me get out my temperature meter and we'll do a load test. Now, where are we going to get heat? You're going to potentially get heat at the terminals. You'll get heat inside the unit. Any bad connection will get heat, or any connection that is small. So what's going to happen at the fuses? They are going to warm up. And I actually know how warm they'll get because I did this yesterday. I have not done it in this exact configuration, but we're going to get at 1000 watts, we're going to get approximately 45 amps here between these cables, and we're going to get about 90 amps here. So this one will get hotter than this one, and then we will just measure it. So let's take some temperature readings here. It's only doing 10 watts, so that's 64 degrees Fahrenheit, 62, 63. You know, this is cold outside, all right? 61, 62, and then we can also test down here. Let's see if the camera can see that. I'll move the camera down a bit. Okay, we'll test here. 62, temperature of the fan, quite cold. 62. All right, so not much. So let's try 600 watts. Okay, there's just the fan, so there's no heat. And let's do 600 watts. You can hear it. There's a whine. Our voltage is dropping down to 12.8, which is to be expected. So we're going to be running, what, approximately 20 here, 20 here, 40 there, something like that. Now let's... All right. See, almost same temperature. Okay. It's just not enough load to heat up, but it sure does at a kilowatt. Okay, let me measure my output fan. It's only come up 1 degree. All right, kilowatt. Okay, voltage here is dropped down to 12.3. The output voltage has dropped down to an AC voltage of 109, so that is coming down. And that's because of the voltage drop on the battery. This does not have a voltage follower where it will boost the output voltage and maintain it super consistent. So now I have to make sure, I'm not going to touch them yet. We're going to see what's going to happen here. So the low amp side, approximately 45 amps. Staying nice and cool. So we're bumped up to, now we're getting warm, okay? So that's 83. You can see that temperature's coming up. All right, 84. And that will continue to rise. So let's check it at the bottom. Nice and cool at the bottom because you've got heavy metal here. But what's happening, oh yeah, that's getting warm. That's as cool as a cucumber because it's half the amps. So this is warming up 90, and this will continue to rise until we reach hopefully a steady state. Now this one will be cooler. Why? Same current, and that's because we don't have a fuse here. And when you have a fuse, so you are going to have a power loss, and I can measure the power loss. So let's do that next. All right, let's set up our voltmeter. Read that. I don't know if we can read that. We are at 0 volts here. Let's measure at the terminal. So we've got from here to here. So that is 12.53. Now we're going to measure to here. 12.37. That is to be expected. What is going on? So let me do the math. The difference between 12.53 and 12.37. All right, the inverter just shut down. I had to unplug it. I got a loud beep. We had a thermal overload. So the power is off, and I'm showing 116. I have to hurry up and measure these temperatures because they're going to start to cool. So 112. I was doing the math, and I had the thing off, and it shut off. So if we go back, there's a kilowatt. I can probably get it to fail. It's going into thermal shutdown. Let's see. But this is a little bit more than this inverter can handle. So anyway, these are starting to warm up. I had like 121 before the failure. So they're already cooling down. But they'll have to warm back up. So it takes a bit of time to warm back up. So that's 92, 100, there we go, 122. See, now that's starting to get warmer. That's what I'm feeling in my finger. And that's because of the inefficiency going through a fuse. Because on this side, look at the temperature difference. So yes, you are going to get, there we go. We're in overload. So the output voltage is 0. So I'm going to shut it off. I have this power shut off, but I want to cool quickly. So what I'm going to do is I don't want to fry my MOSFETs or whatever they have in there, so I quickly shut that off. We have no power going through here, and I want to cool my inverter down. So at least I know what's going to happen here with this mystery inverter. It is going to go into a thermal shutdown at about 1100 watts or something like that. So here's the summary. At 100 amps, I'm showing a 15 watt power loss across the fuse, and I got a temperature of about 122, and that was probably about 10 minutes or something like that. At lower amps was hardly any power loss at all. It stayed nice and cool, but it does get warm. But there was no failure. The plastic did not melt, the fuse did not blow, and everything is as it should. So I was limited into the amount of time I could run based on how long this could do a kilowatt. And in my test, it shut down after about, say, 10 minutes or something like that. So for $15, if you have an application where you have plenty of room to take on a cable, I think it's a good application. If you're doing a parallel connection, then I would probably not use it due to the configuration unless you're using fairly small wires. You can get all kinds of fuses all the way up to, say, 250 amps. And so there's a wide variety of applications and fuse sizes that you can use. And so from that standpoint, it is quite versatile. So I think it is a decent product. It has a lot of advantages and a couple of disadvantages. So that's it for today, and I'll see you next time.